So what we're going to do here is look at the relationship between a confidence interval and a hypothesis test. So let's look at some data. And so here's our sample, blah, 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 blah. And I can generate a bootstrap distribution. It's centered around the sample mean. And we can find, if we click on two-tail, we can find basically the mean plus or minus 2 standard errors. Okay, so 95% of the data lie between 27.329 and 30.932. Okay. If I were to say, I assume that the population mean is 30. Okay. Does this confidence interval support that? Well, 30 is within this 95%. So since it's in that confidence interval, it seems reasonable that 30 could be the true mean. Okay? So if we find the confidence interval and say, we're pretty sure the true population mean is in there, and 30 happens to be in there, well then, yeah, that seems reasonable. What if we took a value like, say, 32.5? All right. So 32.5 is way out here. It's not in the confidence interval. So if I said, what if I said, I think the true mean is 32.5? Well, I've got a confidence interval that's between 27.329 and 30.932. 32.5 is completely outside of that. So it would seem, actually, that my confidence interval would suggest that the mean is actually lower than 32.5. Okay, so if I'm pretty sure that my true population mean is within these two values, and 32.5 is well outside there, maybe 32.5 isn't a good assumption to make. Well, how does that look when we do an actual hypothesis test? So let's go to our test for a single mean. And we get that same data. Okay. And I'm going to change our null hypothesis to, let's say, 30. Okay, hit enter. So I'm going to generate the randomization distribution. So we're taking samples of 500 from a population with a mean of 30. Does this sample mean, what does it tell us? Well, if we did a left-tail test, where is the value 29.11? Well, to get a value that extreme, the p-value is 0.175. That's relatively large. Okay? If we're looking at a statistically significant level of 0.05, 0.175 is greater than 0.05, so we would fail to reject the null hypothesis. 30 seems like a perfectly good assumption for the mean commute time, which was what we're looking at. Now, what if I change that to 32.5? Okay, so before, what we said was, well, based on the confidence interval we got from our sample, 30 seemed a reasonable assumption for a population mean because it was within the confidence interval. 32.5 didn't seem reasonable because it was well outside. Okay, so let's say we'll use the null hypothesis that the mean is 32.5, and we'll take a left-tailed test. The alternative is that it's less than 32.5. Okay, so we can generate our randomization distribution, and what happens with a value of 29.11. So what's happening, what we're saying is, let's assume the mean is 32.5. What are the chances of getting this as a sample mean? Well, way down here, p-value of 0.000. So the chances of that happening very, very, very unlikely, which are basically the same results as we got when we did the confidence interval. The confidence interval did not contain 32.5. In fact, the confidence interval was completely below 32.5. So here, we would be rejecting this null hypothesis of 32.5 and going with our alternative hypothesis, which was, no, the mean is less than 32.5. Okay? So confidence interval, hypothesis test, kind of get at the same information. The hypothesis test works on an assumption. We're assuming some null to be true. Does our evidence suggest otherwise? With the confidence interval, we're basing it on the sample. Okay, so they're slightly different. Okay, the hypothesis test has a little bit more rigor because we're making an assumption, and based on a sample, what does that say about the assumption? But still, the results are the same.